Hey, this is Mr. A, and this is Pre-AP Chemistry, and we are still in Unit 9 gases, but we are in Week 20. What's going on in Week 20, do you say, is we're going to take a look at the kinetic molecular theory, we're going to take a look at deviations from ideal behavior, and we are going to take a look at partial pressure of gases. So let's start off with the kinetic molecular theory, the KMT, which this kinetic molecular theory is dealing with ideal gases. Ideal gases. This is when we can use PIV-NERT. Our ideal gas law is when we can assume each one of these four things. We are assuming that gases are randomly moving with high kinetic energy. We assume that gases have negligible intermolecular attractions, which means these gas particles do not attract each other. That gases have negligible volume. We've talked about that before, that the volume is the volume of the container, not the volume of each individual particle, and that gases are making elastic collisions, which means they do not lose energy when they collide. So how would we have a quote-unquote real gas, a not ideal gas? Well, gases at low kinetic energy, right? Gases where the attractions are actually mattering. Gases where the individual particles' volumes are actually mattering, maybe at really small volumes. And also, when are these collisions losing energy? That's when we have what's called a real gas, a non-ideal gas. But the kinetic molecular theory is something that we can use as a model for all of our ideal gases. When are we going to deviate from ideal behavior? When is this going to be a real gas or a non-ideal gas? Is three things. At a low temperature, that's when the average kinetic energy is getting lower. Those particles are moving slower, which means, guess what? The attractions are starting to matter more, right? At really high pressure, what's happening at very high pressure? Well, the attractions between the particles are becoming greater. The individual volume of the particles actually matter. And of course, at high intermolecular forces, when there's a lot of London dispersion forces, that's when there's very polarizable electron clouds, that is when we stop becoming an ideal gas law, and it becomes very difficult. We can't be using our PIV-NERT equation, and our pressure and different calculations are being thrown off because we are becoming a real gas. This is becoming a real gas. You can see at high pressure right here, at high pressure, the gas molecules, you can see the individual particles are actually mattering. They're colliding. They're attracting with each other. You can see in a real gas, it might be losing energy, and you can see the gases will become a liquid at one point. Okay. Last, we're going to take a look at what's called partial pressures of gases. And that means gas pressure is proportional to the number of particles. It's proportional to the number of particles. So let's take a look at AlCl3. AlCl3 gas. And if you can see, I have 1, 2, 3, 4, 5, 6, 7 particles. I have 7 particles of AlCl3. Here we have Al2Cl6 gas, and how many of these gas particles do I have? 1, 2, 3. 3, which means I have a total number of gas particles of 10 gas particles, which means 7 out of 10 gas particles are the AlCl3. 3 out of 10 gas particles is the Al2Cl6, 70% and 30%, which means if I know the total pressure of the gas inside the container is 15 atmospheres, I can take a look at 15 atmospheres times 7 parts out of 10. It is a proportional relationship here. I know that 10.5 atmospheres is going to be this pressure, what we call this partial pressure, Whereas 15 atmospheres times 30%, or 3 out of 10, 15 times 3 out of 10, is going to be 4.5 atmospheres. So this partial pressure is 4.5 atmospheres. You can see if you add these two up, they add up to 15 total atmospheres. And so the pressure is proportional. The pressure is proportional. If you forget how to do this, you can easily simply do a proportion just like we've always done. You can see we have 7 particles of AlCl3. We have 10 total particles. The total pressure is 15 atmospheres. And you can find the pressure of just one of them by doing cross multiplication. It's the same as doing a ratio. It's the same as doing a percentage. It's the same as doing a proportion. And so the partial pressure of gases is proportional. And that's week 20, unit 9 gases. See you later, alligator.